Hi, everyone. Welcome back to the OnTrack podcast. This is Judy Warner. It's a delight to be back with you this week. And today, as usual, I have an extra special guest, but this one, I swear, is truly extra special. Today, we talk to Dr. Todd Hubing, who is an absolute EMC expert. I can't wait to tell you about him. He's going to teach you about some commonly held myths and ways you might be tripping over some things you didn't know about. So lean in, enjoy. I'll see you on the other side. Welcome to Altium's OnTrack podcast, where we talk to leaders about PCB design, tackling subjects ranging from schematic capture all the way to the manufacturing floor. I'm your host, Judy Warner. Please listen in every week and subscribe on iTunes, Stitcher, and all your favorite podcast apps. And be sure to check out the show notes at altium.com/podcast, where you can find great resources and multiple ways to connect with us on social media. Well, hi, Todd. Thank you so much for joining us today. It is truly a delight to have you and learn about all your expertise in EMC.
It's a pleasure to be here.
Well, you know, we share a few common friends. I noticed we have 140 common friends on LinkedIn. And as I look through that list, we really do share friends and not just connections. And some of those are, you know, Rick Hartley, Dan Beaker, Steve Sandler, Ken Wyatt, all wonderful people that are doing great things in educating design engineers. And it's sort of amazing to me that you and I have ever met. So thank you so much for joining, and we really appreciate the work that you are doing at Learn EMC.
Oh, thank you.
So how about 2020, crazy year? I bet you it changed the courses that you offer at Learn EMC. And in a minute, I'm going to embarrass you and tell our audience about your background.
All right. Yeah, it certainly did have a big impact on our business. We went basically completely online. And we had been doing online before, so it wasn't that big a transition, but the amount of online courses has just skyrocketed.
Yeah, I think we're all right there with you. Well, for our audience, I want to take a moment just because it's worth saying, and maybe it embarrassed Todd for a moment, and tell you about his credentials and the kind of depth of expertise. So bear with me for a moment while I read his bio. That, by the way, I had to shorten. So his bio says Dr. Todd Hubing is a professor emeritus of the electro and computer engineering at Clemson University and president of Learn EMC. Dr. Hubing holds a BSEE degree from MIT and an MSEE from Purdue University and a PhD from North Carolina State University. He was an engineer at IBM for 7 years and a faculty member at the University of Missouri-Rolla for 17 years before joining Clemson University in 2006. At Learn EMC, he provides EMC instruction, consulting, and design assistance to engineers working in the automotive, aerospace, and consumer electronics industry. Dr. Hubing has authored or co-authored over, ready for it, 200 papers and presentations on electromagnetic modeling, electromagnetic compatibility, and the design of reliable electronic systems. He is a fellow of the Institute of IEEE, a fellow of the Applied Computational Electromagnetic Society, that's a mouthful, and a past president of the IEEE Electromagnetic Compatibility Society, or EMC Society, or am I saying that right? Yeah, EMC Society. So again, wanted to sorry to embarrass you by your own credentials if I have, Todd, but I wanted to let our audience know the depth of, you know, academic weight behind your learning, as well as this really neat, I think, place you filled sort of between industry and also academia. So, you know, in regards to that, what would you say, as you've spent so many years doing this, you know, how that background serves you, and sort of why you decided in these latter years as a business owner and consultant, how's that how are those things different, and how they sort of dovetailed on one another as you teach courses online and maybe one day in person at Learn EMC?
Well, certainly, as far as teaching courses, I don't see how you can possibly teach electromagnetic compatibility unless you were actively engaged in the field, working with people who were designing products and having EMC problems. There's only so much only so far that the theory will take you, and the theory is
Right.
important. It is very important. But on the other hand, knowing what trade-offs need to be made and when trade-offs don't need to be made in particular, that really can only come from working with specific products and gaining that experience. And also communicating then with the other people who are also doing the consulting and their experiences. It's just very important in electromagnetic compatibility.
Well, for our listeners, I wanted to just pause here a minute and let you know we're going to put loads of resources behind in case you had to jump off early today. We're going to connect you to Dr. Hubing's Learn EMC website. There's so many resources there. So whatever we don't cover in a short podcast, there's rich resources for you, as well as information on his classes. He does something really neat called the EMC question of the week. And he's been doing that. How long have you been doing that, Todd?
For just over 4 years.
So he started, I think he said back in March of 2017. And recently, what drew my attention to him this past week or two is that I saw on LinkedIn he had published a book. So he took all those questions from March 2017 to December 2020 and published them in a book. And I think there's a lot of really practical learning there. So I'm going to put a link to that. And also he has over 30 years of learning between his academic and theory and his hands-on in industry. And there's a wonderful EMC design guideline collection, including the top 4. So you're going to go after that. So tell us a bit about sort of all the offerings of Learn EMC, and then we're going to jump into sort of these 4 myths that seem to trip people up as you do your consulting business.
Oh, okay. Yes, so we offer short courses in EMC, basically various topics related to electromagnetic compatibility, and I do consulting through Learn EMC. So. Of course, all of that's been online. We have a nice facility here in Stoughton, Wisconsin, and prior to the pandemic, people would come to Stoughton, Wisconsin, and we would teach these courses, or often I would go to the company and teach courses. But we also did a lot of online stuff even prior to the pandemic, primarily for people on other continents, where it just made economic sense to do it online.
Right.
Yeah, but with the pandemic now, everything we offer is online. It's all been live online pretty much, other than what's on our website, but we are working on developing asynchronous online instruction so that people can sign up for a course and then take it at their leisure.
Well, I kind of got a kick out of, again, today I feel at a distinct disadvantage as I know less about EMC than other parts of design engineering, but it was really neat to see some of the equipment that you have there to show how to do these measurements. And it's really impressive to see that, because for me, I feel like I'm going to another planet with the look of all that sort of almost sci-fi looking equipment to me anyway. So certainly with the proliferation of IoT, as well as communications, automotive, and so many other sectors, EMC seems like it's bigger than ever. It's more important than ever for design engineers to understand. So let's jump into these 4 things that I'm saying are kind of myths, but maybe you want to tee them up in a different way, but maybe commonly held beliefs that may or may not be true. So let's jump into the first one that is about solid ground plane should be gapped between analog and digital circuits. So dig in there and give us some insight.
Yeah, so that's one of the design guidelines on our collection of EMC design guidelines that we have on our website. And we sort of categorize those design guidelines in terms of pretty good design guidelines and not so good and just terrible. This being one of the terrible ones. And so, yeah, don't gap a ground plane. Actually, one of the good ones is don't gap your ground plane. The plane that you've called ground, which is really a current return plane, don't gap that. There's never a good reason to do that. And even though I have been saying that for years, Rick Hartley, Dan Beaker, Ken Wyatt, everybody's saying that. And yet, when people bring me designs, quite often they've gapped the ground plane. They're convinced that in their special situation, it was the right thing to do because of, and because of often is guidelines that existed 40 years ago, which weren't actually even very good design guidelines then. But anyway, yeah, you should, people see analog, digital, they think they can't share the same current return plane. And that is almost never true in real products. You can, I have several examples in the class where we show, okay, here's something that's switching a solenoid and it's pumping 10 amps of current, you know, with a spike with a 1 microsecond rise time, and it's using that ground plane to carry that current. And here's your 1.2 volt digital circuitry over here. You can share the same plane. If you do the calculation, you can share the same plane. And there are some situations where you can allow currents to share the same plane, but you should never assume they have to be isolated. It's a simple calculation. You take the worst case current from your source, multiply that by about a milliohm, which will be the shared resistance worst case in most planes. And that voltage that you get, so 10 amps would become 10 millivolts, that's your worst case common resistance coupling. And that's the only reason. If 10 millivolts was too much, then we'd say, okay, I can't share the plane. But even then, I wouldn't split the plane. We would want to route the return, whichever return was easier to isolate. We would want to route that return on a different layer, but not split a solid plane into two parts. And by the way, that's only for low frequencies. At high frequencies, the currents will come back right under the trace if we've routed things well, and we won't have common impedance coupling anyway. So are there situations where we want to isolate the return? There are some, but not nearly as many as people think. And when we don't want to split the plane.
So, you know, I've talked to both Rick Hartley and Dan Beaker about these sort of, maybe because it's old. In your mind, you say, you know, obviously technology is advancing and the parameters are different, but what causes that lack of understanding to sort of persist in the market?
Well, I think Eric Bogatin's fond of saying it's hard to unlearn something. And I think a lot of these people, especially people my age or close to my age, we learned that. That was the rule back 40 years ago, 30, 40 years ago. And it's hard to unlearn things like that. And also a lot of things that you learn from doing an experiment are hard to unlearn, even if they're wrong. I had a lot of that knowledge coming out of IBM. We'd see a problem and we would do something that fixed the problem. And in our own mind, we'd think, okay, next product that comes, we're going to do that thing. We're going to do it that way. And even though it worked for that product, it wasn't the right thing to do. And it made things worse, perhaps on future products. But I think a lot of this splitting planes, I've seen boards that have 4 or 5 different what they call grounds on their board, and that's never justified. And it can be a large problem because having 4 or 5 different high frequency grounds is ultimately our source for a lot of radiated emissions problems.
The next one I want to cover with you, Todd, is one I've definitely heard Rick Hartley talk about, is the decoupling capacitor should be located as close as physically possible to the IC's power pin.
Yes, so that's the design guideline. And in many situations, that's exactly the right thing to do. But in many other situations, that is exactly the wrong thing to do. I have seen designs where they have a ball grid array with 300 pins, a dozen of them are power pins, and they're trying to cram decoupling capacitors either up into the pin field of the ball grid array, or they're putting them on the back of the board right underneath
Yes.
the device. And those decoupling capacitors are not contributing so well, depending on how you've laid out your board now. So if you have a ball grid array with 300 pins and you've got, say, 14 layers in your board, and you put the decoupling capacitors on the backside, the ball grid array is going to be drawing most of its charge from the power ground plane pair that is closest to the top. And you should have one close to the top if you were getting your stack up right. So the ones on the back side, they're connected through too much inductance to contribute very well compared to the ones that are connected on the top side. And on the top side, it really doesn't matter how far away they are within reason. We'll often hear people say, oh, we have to worry about the time of flight. So I need charge in 50 picoseconds, so I can only get that from things that are located so far away.
Yes.
And in real boards, I mean, again, you might want to do the calculation or do the simulation to convince yourself. But in real boards, the inductance of the connection to the planes is so high, you're not going to get the charge that fast from anything connected to the planes anyway. The best source of charge right away is the planes themselves, and you will continue to draw charge from the planes as fast as the planes can provide it. And eventually the decoupling capacitors start to kick in and help, but that eventually is hundreds of picoseconds or nanosecond or more. And when you do simulations and you look at the ones that were close versus the ones that were farther away, the ones that were close were not providing substantially more charge than the ones that were far away.
Interesting. Well, I remember talking to Lee Ritchie or him teaching and, taking this little red wire. I think sometimes design engineers can lose, and I'm interested in your thoughts here, a picosecond, the distance it takes, physically. And sometimes I think it's easy to lose sight of what that is. And and as far as, is this an area you've talked to me about? This is, again, all the brilliant guys you've mentioned, as well as I think Lee Ritchie, who started it, is to never trust an app note. Is this something that gets sort of served up through the app notes?
Yes, when an app note shows, tells you, if people are putting them on the backside underneath the ball grid array, that is often because of advice they've seen in an app note or a trade magazine publication, something like that. And there are situations where that's the right thing to do.
Yeah.
It's not all situations. If you've got a 300 pin ball grid array and a 14 layer board, the odds are those things on the opposite side are not helping. But in other stack ups, other situations, that may be the right thing to do. But yes, when people are doing it wrong, when people have two decoupling capacitors, one of them is 1 microfarad and one of them is 0.001 microfarads, and they're both in parallel, that is not a good thing to do. And why would anybody do that? It's because they read that in the app note usually.
So on your design rule guidelines that are on your website, do you go into more depth? Like, I'm thinking about our listeners. Okay, do it sometimes. Well, when do I do it and when do I not? And is it simply about calculating? I mean, how do I know if I'm design engineer, when to practice that and when to not?
Yeah. So I would say learning design rules or design guidelines is a terrible way to learn how to design a board. Design guidelines can be useful, but I think I say even on our website that the worst designs I've ever seen were done the way they were done because people were trying to follow design guidelines. People who know nothing about EMC are unlikely to do crazy things like split a ground plane or put two capacitors in parallel with greatly different values. Yeah, it's design guidelines are more likely to lead people astray. You really, if somebody says, well, how should I do my decoupling then? You can't read.
Got it.
You can't read one little paper or something and know necessarily how to do that. You can take a course, of course.
Well, that's kind of what I'm looking for. So then the thing is to really take a course and get better on the principles of EMC so you don't make those mistakes.
That's right. And it can also help. Sometimes it makes more sense to just work with a consultant on your design, particularly if your designs tend to all be similar. You know, a lot of times I'll work with a company on a design. I always guarantee compliance when I do consulting, and so I'm basically saying, you build it this way, I guarantee you'll meet all of those EMC requirements that you have. So this design will meet all of your requirements. And after they've done that with me, the next design they bring to me looks pretty good.
I see.
And I think it's in some ways it could be more effective to work with somebody on your design, because everything on your design is immediately important to you. So you're going to pay a lot of attention, you're going to learn. Whereas if you just take a course and you're thinking in the future, I may need to use this, you're less likely to absorb.
Right. To retain that with everything else you're doing.
Right.
That makes a lot of sense. And like you say, then, you know, if your designs are similar, it teaches you the principle of that kind of design. So hopefully that carries forward, sort of hands-on, isn't it?
Right.
That's great. So here's the third one I wanted to discuss with you. The myth of, on multi-layer boards, the best stack up is, so we're just going to apply the same stack up template. I know this from being in the bare board industry. Like there's one perfect stack up.
Exactly. I have worked with people who are on their designs, and I'll say, okay, this is what I'm recommending, and I guarantee this will comply with all the requirements. And they'll say, oh, but that stack up is horrible, or that stack up is garbage. And it's because they heard that. They took a course and somebody said, you know what, on a 4-layer board, signal, power, ground, signal is the worst stack up you could make.
Yeah.
And sometimes it is the worst stack up you could have, but a lot of times it's perfectly adequate. And yeah, the idea, so I'll often ask, so what should I have done? And usually that involves, well, you should have, instead of signal, power, ground, signal, you should have had signal, power, ground, ground, signal. Yeah, that could be a very good stack up, but you've now removed a lot of your signal routing area. So did you, if you need to go to a 6-layer board because of you were fixated on that particular stack up, then that's probably not a good idea. I think a lot of, if you come from the aerospace industry, add a couple more layers. You know, it's no big deal to add a couple more layers if you're in the aerospace industry, because the raw cost of the board is not as big a concern as other things. But a lot of my customers, their quantities are in the millions or tens of millions.
Right.
So you add another pair of planes to a board,
Yeah.
that's a severe impact. You want to know that you needed to do that.
Yes.
And particularly on a lot of the 4-layer, 6-layer board designs, the reason we're doing it on so few layers is because we want to keep that layer count low. And if we can do it without having 2 of those layers devoted to ground, then by all means, let's do it that way. If we can't, I mean, I've seen designs where I basically say, I'm not going to guarantee compliance. We need another layer pair because we can't do what you want to do in the number of layers you have. But most often it sort of works the opposite way, that they have plenty of layers. They've just not routed it well. But yeah, with the stack up, 6 layers in particular, yeah, signal, ground, signal, power. Signal is sort of a default layout. That's the one, and 6 layers that people say, well, that's garbage. No, that's perfectly fine. But in some cases, maybe what you need is signal, ground, power, signal, ground, signal. That would, if I had a lot of high-speed circuitry, I had a lot of high-speed signals that I needed to take care of, maybe that would be what I would want to do. Or in others, maybe signal, power, or signal, ground, power, signal. Might be best in that situation. That will usually only be a situation where I haven't got a lot of high-speed stuff going very far, or at least going off the board. But anyway, in some cases, that is the best stack up.
You're reminding me of how many times I've heard Eric Bogatin say, when people come at him with, is it this or that? And his answer is always, it depends. And I think I'm going to link this in the show notes because I think it'll be helpful. Todd, last year, Eric Bogatin, Istvan Novak, Steve Sandler, and Rula Bakla did an EMC panel at Altium Live. And they did that a lot, where they all know it depends.
Right.
And I think you're resonating with that.
Yeah, and that's been a standing joke in the signal integrity and EMC communities probably for decades. But it depends is, yeah, you can argue that's always the right answer. But I argue it's not a helpful answer. And if you're doing EMC consulting, or you're teaching a course to somebody and they want to know,
yeah,
hey, it depends, that's not helpful. It may be correct, but it's not helpful. And
yeah, it doesn't. That's not helpful if you're a design engineer and you've got a deadline and yeah, no, I need the answer. Now I'm wondering, because so often I've noticed on the fabrication side that an OEM or a designer will sort of throw their design over the wall and lean on the fabricator to help them with the stack up. Is there a disconnect that happens there when they're asking for help with the stack up?
As far as defining where the planes are, that, yeah, the fabricator shouldn't be doing that. If you're allowing the fabricator to determine heights and widths in order to meet a
I get it.
Trace,
Yes,
that
yes.
may or may not make sense depending on your specific situation.
Yes, it's typically around those types of subjects. Just wondering. Okay, let's hop to the last one, which is to suppress common mode noise. The power input on a circuit board should have a common mode choke.
Yeah, so I get a lot of designs, and I see a lot in app notes and basically design guidelines, where they're putting common mode chokes where common mode chokes do not belong. And a common mode choke in a place where it doesn't belong can actually create an EMC problem where you wouldn't have had one without it. So basically, if there were a rule of thumb, and we have to be careful about rules of thumbs, but you would only use a common mode in a case where you had a differential, say a differential signal, then putting a common mode choke on a differential signal, especially where it leaves the board, makes a lot of sense. Or on a power input, if both sides of your power are isolated from ground, then you probably, not always, but probably want a common mode choke in there, because now we can actually have a common mode where we send noise out and it returns on ground. But if one side of your power is ground, and in automotive particularly, one side of your power should be ground in most products. Isolating your power return from ground in an automobile creates all kinds of headaches for you that you don't need. There's generally no good reason to isolate the power return from the frame ground. But if you have done that, and the most common reason for doing that I have encountered is the OEM requires it. So that they're just the tier one supplier. They they build the electronics, but I know I don't want to name OEMs, but the OEM required them to do it. So okay, you've got to live with that. It's unfortunate because it was completely unnecessary, and most OEMs do not require you to isolate the ground. So if you've isolated the ground, then you're probably going to put a common mode choke in there. But if you haven't, and hopefully you haven't, a common mode choke is going to just make things worse. It's not going to, it's not the right thing. If you take a common mode choke and something is connected to something labeled ground, you're probably misusing that common mode choke. And especially when both sides, so this was in one of our questions of the week, if both sides are connected to something labeled ground, that's almost certainly a very bad advice. And when you track down where this advice came from, a lot of times it comes from people selling common mode chokes. So,
you need these, and you need more of them because we want to sell them. Well, Todd, these have been really, really helpful. So thank you so much for joining, and I hope you'll come back again and we'll tackle a few more of these, because I'm sure this will be so helpful for our listeners. And I think if I was listening, the advice I'd give is go take some courses at EMC or hire Todd. I don't know that I'd want to navigate these landmines, or, obviously you've spent years and years learning these. So thank you so much for joining us. We appreciate your knowledge so much.
Well, it's been my pleasure.
Well, before I let you go, I want to give our audience a taste of what your EMC questions of the week are. Now, I'm not going to cheat, because by the time this is published, this will have already, you'll have new questions up. But I want to ask you about your question of the week as of this recording, what your question of this week is, and then have you sort of unpack why this is true. Okay, here's the question.
Oh.
I'm going to give you a test, Todd. For a pair, I bet you know the answer. For a pair of identical circuit board traces over a ground plane, the difference between differential mode propagation and odd mode propagation is A, differential mode is undefined, B, odd mode is undefined, C, a factor of 2, D, there is no difference. Okay, Professor Hubing, what say you?
So the correct answer there is no difference. Quite often these questions of the week are related to whatever I happen to be working on at the time, or if I read something where somebody has got something wrong, I try to turn that into a question of the week. Although I've learned from experience, the most popular questions of the week are the ones that are pretty easy. So the ones I feel really great about because they were challenging tend to get less likes on Twitter than the ones that are, what's the difference between an N-type connector and a BNC connector? People really like that. So people like the ones they know the answer to.
Well, that's why I like easy crossword puzzle. It makes me feel really smart.
Yeah. So usually I try to make it so where the answer is relatively easy, especially given the choices you have. But then in the answer that we publish, when you click on it and you see the full answer, it goes into a little more detail. I think many people would recognize differential mode propagation and odd mode propagation are the same, but differential mode impedance and odd mode impedance are not the same. And in many cases, I see odd mode impedance defined in kind of a crazy way where we say we define the impedance on this trace relative to ground when we drive it with this trace. Defining an impedance that depends on how you drive the system in a linear system doesn't make sense. It's not a very rigorous or clear definition. And that made me, when I saw that made me go back and look at some of the old signal integrity books where that even mode impedance, odd mode impedance first popped up. And that's not how they defined it. They defined it, well, actually, I was going to say people could go and look at the answer to that question, although by the time they see this, that answer may not be there. But basically, odd mode impedance is always half of the differential mode impedance. Differential mode impedance is very well defined, and the odd mode impedance is always half that.
Well, again, this has been so fun to learn from you and learn EMC and your deep expertise. For our listeners, part of the reason I have a hidden motive here. I wanted to have you make sure you go over and look at all the answers that Todd and Learn EMC has answered over the year, and maybe take a look at that book. I saw the post on LinkedIn about the book, and several said bought it. So it sounds like something that design engineers would really like to tap into. So make sure you go to the show notes, and you can click through the book if that's interested, or all the many resources that are available on Learn EMC. And also I've put Dr. Hubing's LinkedIn profile. Sounds like he's on Twitter. So I think you'll want to engage with him, because I know he's always serving up good learnings, which is how I stumbled across him, and also his good reputation from common friends. So hopefully, if the audience, if you'd like me to try to talk Dr. Hubing into presenting at Altium Live, let me know, because that's what I'm thinking, wink, wink, that I would love to talk him into, since he's doing online training anyways. It sounds like Altium Live is going to be online. So if you want to hear more from Dr. Hubing, give me a shout on LinkedIn, Twitter, or wherever you have found this. So, Todd, thank you so much again for joining us today. And I hope we can rope you into coming back for another podcast, and maybe I can twist your arm to come do a course at Altium Live.
Yeah, well, thanks for giving me the opportunity. I've enjoyed it.
For our listeners, thanks so much for joining us today. I always ask you to subscribe and like, not because I want you to like us, but because it helps continue to push this out to other design engineers. And we always like to hear from you, and we want to keep serving up what's valuable to you. So thanks for joining us. Thanks for joining us for this conversation with Dr. Todd Hubing. We'll see you next time. Until then, remember to stay healthy, stay safe, and always remember to stay on track.